How is it that the universe can bend, break, or even defy the very rules we thought were unbreakable? Imagine a place where our foundational laws of physics start to crack under pressure, a world of quantum anomalies. What if the universe isn't just stranger than we imagine, but stranger than we can imagine? Buckle up as we explore these mysterious breakdowns in symmetry that reveal gaps in our knowledge and challenge our understanding of everything from matter and energy to the cosmos itself. At the heart of quantum mechanics lies a world where particles don't behave as we might expect from everyday experience. Objects at the quantum scale can exist in multiple states simultaneously, pop in and out of existence, and exhibit properties like spin, charge, and momentum in strange ways. This world is governed by symmetries, principles that suggest certain properties stay the same even as particles move or interact. However, anomalies arise when these symmetries appear to break under certain conditions, creating a paradox for physicists to untangle. Anomalies are significant because they provide hints of deeper, often hidden, layers of physics that don't fit neatly into established theories. For example, theories like quantum electrodynamics, which describe how light and matter interact, or quantum chromodynamics, which describes the strong force within atomic nuclei, assume that certain conservation laws will always hold. Conservation laws, like the conservation of energy, momentum, and charge, are seen as cornerstones of physics. However, when anomalies appear, they indicate situations where these laws don't behave as expected, signaling that our theories may be incomplete. Understanding anomalies can also reveal why certain particles and forces act the way they do. They give scientists clues to explore unknown physics beyond what we currently understand. For instance, the Standard Model of Particle Physics, the best framework we have to describe the universe's particles and interactions, doesn't fully account for phenomena such as dark matter, dark energy, or even gravity on the quantum level. Quantum anomalies sometimes hint at new physics that could bridge these gaps, potentially pointing to new particles or forces. In this video series, we will explore 4 primary anomalies and then cover a few additional examples to broaden the picture of quantum anomalies in the universe. Each anomaly is linked to specific types of quantum fields or forces, yet all share the underlying mystery of broken symmetry. Each anomaly is like a glitch in the physical laws, giving us clues to unravel deeper truths about nature. Anomalies are also a valuable guide for building new theories, as they highlight exactly where existing theories might need adjustment. For instance, anomalies related to chiral symmetry breaking have spurred research in particle physics, influencing everything from the study of neutrinos to understanding the early universe's conditions after the Big Bang. Anomalies also have practical importance. For instance, the quantum anomalous Hall effect, which involves electrical conductivity in special materials, is an anomaly that has direct applications in developing next-generation electronics and quantum computing technologies. To make sense of quantum anomalies, scientists rely on quantum field theory, a framework that blends quantum mechanics and special relativity. Quantum field theory is essential for understanding particles as excitations in quantum fields, which are the foundational elements of matter and forces in the universe. However, quantum field theory isn't flawless. Many anomalies highlight limits in quantum field theory, such as the challenge of integrating gravity within this framework, as shown by the Gravitational Anomaly. Addressing these anomalies could pave the way for a more unified theory of physics, often called a theory of everything. These mysteries are crucial not only for high-energy physics, but also for fields like condensed matter physics, cosmology, and even information science. Quantum anomalies are studied in laboratories worldwide, with experiments examining how particles behave under extreme conditions. The insights gained from these studies can reshape our theories of matter and energy, and one day they might lead to breakthroughs in technologies we can't yet imagine. In the following sections, we'll explore each major anomaly in detail, starting with the quantum anomalous Hall effect. With each anomaly, we'll discuss the strange behaviors observed, what they reveal about fundamental physics, and how they might help us solve open questions in science. The quantum anomalous Hall effect is a phenomenon that bridges classical and quantum physics in a unique way. At its core, it involves a specific behavior of electrical current in materials when exposed to magnetic fields. But what sets it apart is that it occurs without the need for an external magnetic field. Instead, the properties of certain materials cause this effect naturally, making it an example of a quantum anomaly, a situation where classical laws and quantum mechanics reveal surprising, sometimes puzzling, differences. To understand this anomaly, it helps to start with the classical Hall effect, which dates back to 1879. In the classical Hall effect, when an electric current flows through a conductor in the presence of a perpendicular magnetic field, the electrons are deflected to one side due to the magnetic force, creating a measurable voltage on either side of the material. This lateral separation of charge is known as the Hall voltage. The Hall effect has many uses in modern technology and research because it allows scientists to measure the nature and density of charge carriers, such as electrons or electron-like particles, within a material, took the classical Hall effect into the quantum realm. It occurs in very thin, two-dimensional materials exposed to extremely low temperatures and strong magnetic fields. Under these conditions, the behavior of the electric current is quantized, meaning it takes on specific, discrete values rather than varying continuously. This quantized Hall conductance is directly linked to fundamental constants of nature, like the charge of the electron and Planck's constant, which is central to quantum mechanics. The discovery of the quantum Hall effect earned a Nobel Prize and transformed how physicists understood the behavior of electrons in low-dimensional systems, setting the stage for further explorations into quantum phenomena. However, the quantum anomalous Hall effect diverges from this standard pathway. In this anomaly, the quantum Hall behavior occurs without any applied magnetic field, relying instead on the intrinsic properties of the material itself. The materials that exhibit this effect are typically magnetic and possess an unusual internal structure that mimics the action of an external magnetic field. This internal structure is called a magnetic texture, a unique arrangement within the material that causes electrons to behave as though they were in a strong magnetic field, even when no actual magnetic field is present. One way to understand the quantum anomalous Hall effect is by looking at the role of spin, a fundamental property of electrons and other particles. Spin can be thought of as an intrinsic type of angular momentum that particles possess. In certain materials, the spins of the electrons are aligned in a particular way, creating an overall magnetic field within the material, often referred to as a magnetization. This internal magnetization, combined with the material's specific electronic properties, can give rise to the quantum anomalous Hall effect. In this context, the material's band structure plays a critical role. The band structure of a material is essentially the arrangement of energy levels that electrons can occupy. In most ordinary materials, electrons fill the available energy bands in a predictable way, which governs how they conduct electricity. However, in materials exhibiting the quantum anomalous Hall effect, The band structure has a particular shape that allows for electron states with a fixed orientation or chirality. This chirality restricts the movement of electrons to one direction around the edge of the material, a phenomenon known as edge conduction. Electrons with different chiralities or directions of movement are restricted to separate paths, preventing them from scattering across the material and allowing the electric current to flow smoothly along the edges. This is a hallmark of the quantum anomalous Hall effect and is what gives this anomaly its unique behavior. What makes this effect especially remarkable is that it reveals how quantum mechanics can produce effects usually associated with strong magnetic fields in a material's structure alone. In a sense, the quantum anomalous Hall effect is an example of a material acting like a magnetized conductor without needing a magnetic field from the outside. The effect is closely tied to something called topology in physics, a way of classifying different types of electronic states based on how they behave under various conditions. Materials with topologically unique electronic structures are called topological insulators. These materials conduct electricity only on their surfaces, not in their interiors, and when magnetized, they can exhibit the quantum anomalous Hall effect. One critical fact about this anomaly is that it requires materials with very specific properties. Scientists have developed these materials in the lab, primarily using compounds that combine elements such as chromium or other magnetic materials with elements like tellurium. The resulting compounds often need to be cooled to extremely low temperatures for the quantum anomalous Hall effect to manifest clearly. Currently, much of the research into this anomaly focuses on finding materials that can exhibit the effect at higher temperatures, as this would make it more practical to observe and study. The quantum anomalous Hall effect also provides insight into symmetry in physics. Symmetry is a concept that describes how physical properties of systems remain constant under certain transformations, like rotation or reflection. In classical physics, symmetries are often straightforward, like how a sphere looks the same from all angles. However, quantum systems often exhibit more complex symmetries, which can break down in unique ways, leading to anomalies like the quantum anomalous Hall effect. In this effect, a particular type of symmetry called time reversal symmetry is broken. Time reversal symmetry suggests that the fundamental laws governing a system's behavior should remain the same if time were to flow backward. In magnetic materials showing the quantum anomalous Hall effect, this symmetry doesn't hold due to the internal magnetization, which effectively chooses a particular direction for the electron spins. This choice results in a directional flow of electric current that can only exist along the edges of the material. Another essential aspect is the precision with which the quantum anomalous Hall effect can be measured. In experiments, scientists have observed that the electric current in materials showing this effect takes on quantized values, with conductance levels determined by fundamental constants. This accuracy is due to the quantum mechanical nature of the effect and makes it an ideal system for testing the limits of quantum theory. By studying the quantum anomalous Hall effect, researchers gain valuable insights into how particles behave in low-dimensional systems, how quantum mechanics governs the motion of electrons, and how symmetry breaking processes shape the behavior of matter. The Chiral anomaly is a unique and somewhat counterintuitive phenomenon in quantum mechanics that highlights the ways symmetry can break down in unexpected circumstances. This anomaly reveals how certain fundamental laws in physics do not always behave as we expect, especially when particles interact in high-energy environments, such as particle accelerators or the early universe. The chiral anomaly plays a significant role in theoretical physics, as it influences our understanding of particle behavior under extreme conditions, specifically those related to chirality and how symmetry is broken in the process. To understand the chiral anomaly, we must first understand the concept of chirality itself. In physics, chirality describes a property of particles where they can have a specific handedness, a distinction between left-handed and right-handed configurations. Chirality is similar to the concept of handedness in everyday life, just as your left and right hands are mirror images of each other, but cannot be superimposed. Certain particles in quantum mechanics exist in forms that are mirror images, but cannot be interchanged. This property is essential for particles like neutrinos, electrons, and quarks, which can have distinct left-handed and right-handed states. In particular, particles such as neutrinos exhibit only one type of chirality, always being left-handed, which is why chirality is especially significant in particle physics. The chiral anomaly occurs when certain symmetries related to chirality, those that we expect to hold under typical conditions, break down. These symmetries relate to specific conservation laws, particularly for particles with well-defined left or right-handed states. Under normal conditions, the numbers of left-handed and right-handed particles should be conserved separately. However, in certain quantum processes, these conservation laws fail to hold, creating the chiral anomaly. This breakdown is surprising because conservation laws are seen as foundational principles of physics, and their apparent violation hints at deeper, often hidden, mechanics within quantum theory. A key to understanding the chiral anomaly lies in the behavior of particles when they are exposed to strong electromagnetic or other force fields. One of the simplest examples is the behavior of electrons, which are charged particles. When electrons are placed in both a strong electric field and a strong magnetic field, a current of electrons starts to flow, creating an electric current. The behavior of these electrons can be analyzed in terms of chirality, or their left-handed and right-handed components. In situations where only a magnetic field is present, the number of left and right-handed electrons is usually conserved. However, when an electric field is introduced, along with the magnetic field, the electrons are forced to behave in a way that breaks the conservation of chirality, causing a net imbalance between the left-handed and right-handed electrons. This is the essence of the chiral anomaly, a breakdown of chirality conservation when certain external forces act on a quantum system. In technical terms, the chiral anomaly can be understood through quantum field theory, the theoretical framework that describes particles as excitations in quantum fields. In this theory, particles with chirality are associated with fields that transform in particular ways under rotations and other transformations. These transformations, known as symmetries, are supposed to protect certain properties, like the conservation of left-handed and right-handed particles. However, the presence of strong fields changes the way these transformations work, causing an imbalance in the numbers of particles with different chiralities. This is known as anomalous symmetry breaking because it contradicts the expected symmetry in the quantum field equations, resulting in the violation of chirality conservation. One of the classic cases where the chiral anomaly appears is in the interaction of quarks and gluons. Quarks are the fundamental particles that make up protons and neutrons, while gluons are the particles that mediate the strong nuclear force between quarks. This force, which holds atomic nuclei together, is governed by a quantum theory called quantum chromodynamics, or the theory of strong interactions. Within this framework, quarks possess chirality and can be either left-handed or right-handed. In the presence of extremely intense gluon fields, fields that can occur in conditions like those of the early universe or in high-energy particle collisions, the chirality of quarks can be altered. The conservation of chirality that would usually hold does not apply in these extreme conditions, leading to the appearance of the Chiral Anomaly. Another notable manifestation of the Chiral Anomaly can be observed in the behavior of neutrinos. Neutrinos are nearly massless particles that interact only weakly with other particles, making them difficult to detect. Interestingly, neutrinos exhibit a unique chirality, existing only in left-handed states, while their antimatter counterparts, antineutrinos, exist only in right-handed states. This peculiar behavior plays a role in weak interactions, the type of force responsible for processes like radioactive decay. The Chiral anomaly helps explain why certain symmetries do not apply to neutrinos in weak interactions, where the chirality of particles is a defining characteristic. Because of the Chiral anomaly, we understand that the universe favors certain interactions that align with the chiral structure of particles, an insight that has influenced studies in particle physics and cosmology. Mathematically, the Chiral anomaly is represented by a term called the axial current, which describes the flow of particles with a particular chirality. In an ideal situation without anomalies, this axial current is conserved, meaning the number of left-handed and right-handed particles remains constant over time. However, when anomalies are present, the axial current is no longer conserved. This non-conservation is precisely what defines the Chiral anomaly, a change in the axial current that indicates a shift in the numbers of left and right-handed particles due to quantum effects in the presence of external fields. The study of the chiral anomaly also has deep implications for our understanding of the early universe. Shortly after the Big Bang, the universe was a hot, dense state filled with high-energy particles interacting with one another. In these conditions, intense fields, such as those associated with the strong nuclear force, would have influenced particle behavior on a grand scale. The chiral anomaly suggests that under these high-energy conditions, the conservation of chirality may not have held, leading to an imbalance in particle properties. This imbalance may have contributed to processes that shaped the universe's evolution, including the distribution of matter and antimatter. In fact, certain theories propose that the chiral anomaly could have played a role in the dominance of matter over antimatter, although this idea remains an area of ongoing research. One of the most striking aspects of the Chiral anomaly is how it bridges the classical and quantum realms. In classical physics, conservation laws, such as those governing the number of particles, are rarely questioned. However, the Chiral anomaly shows that quantum mechanics can introduce situations where these classical ideas no longer hold in the same way. This anomaly also illustrates the limitations of symmetry in quantum systems, highlighting how symmetries can be respected in certain situations, but broken in others, depending on the presence of external fields or high-energy interactions. This makes the chiral anomaly a powerful example of how quantum physics reshapes our understanding of fundamental principles that otherwise seem universal in classical contexts. The conformal anomaly is a unique phenomenon that arises within the field of quantum field theory, a framework that describes how particles and fields interact at the smallest scales. This anomaly reveals the breakdown of a certain symmetry called conformal symmetry, which is an advanced concept of symmetry related to scale. Scale symmetry implies that the behavior of a system should remain unchanged even if we alter the distances or sizes of objects within it. In physical terms, if a theory has conformal symmetry, then changing the scale of space and time would not change the basic behavior of particles and fields within that theory. However, The conformal anomaly highlights instances where this symmetry does not hold, indicating that scale invariance can fail in quantum systems. This anomaly challenges our understanding of fundamental symmetries in physics, as it reveals gaps in how scale symmetry operates within the realm of quantum mechanics. In classical physics, scale invariance is straightforward. If a system behaves the same regardless of its size, then the theory describing that system is considered scale invariant. For example, if we observe a galaxy cluster from a large distance and then zoom in on a single part of it, the overall structures of stars and galaxies appear similar at different scales. Similarly, conformal symmetry in physics would mean that a field or particle interaction looks the same, no matter how large or small the distances or energy levels. However, in quantum field theory, scale invariance does not always hold because quantum effects can interfere with this symmetry. This interference is where the conformal anomaly becomes relevant. The conformal anomaly arises because, at the quantum level, certain forces or fields behave in ways that disrupt scale invariance. One way to understand this is through the behavior of energy. In quantum field theory, energy plays a crucial role, and particles interact by exchanging quanta of energy. When these energy exchanges occur within a scale invariant system, the behavior of particles should, ideally, remain consistent regardless of the energy level. However, quantum corrections, small adjustments made to account for quantum fluctuations and uncertainties, often disrupt this balance. These quantum fluctuations, which reflect the inherent unpredictability of particles at the smallest scales, can introduce terms into the equations that break scale invariance. This breakdown of scale symmetry at the quantum level is known as the conformal anomaly. One of the central ideas behind the conformal anomaly is the concept of renormalization, a process used in quantum field theory to handle the infinite values that sometimes arise in calculations. Renormalization involves adjusting the parameters in a theory, such as masses or charges, to account for quantum effects and make calculations finite and manageable. However, the process of renormalization itself can disrupt scale invariance, leading to the conformal anomaly. When the parameters are renormalized, the theory often ends up losing its original scale invariance, which means that changing the scale of space or energy results in a different behavior of the system. This shift in behavior indicates a loss of conformal symmetry, giving rise to the conformal anomaly. In addition to renormalization, another way to understand the conformal anomaly is by looking at the stress energy tensor, a mathematical object that represents the density and flow of energy and momentum in a system. The stress energy tensor is a critical concept in both classical and quantum theories, as it describes how energy is distributed and conserved within a field. In a conformally invariant theory, the stress energy tensor should ideally have certain properties that make it traceless, meaning that its sum along certain dimensions is zero. This traceless property signifies that energy and momentum are evenly distributed across scales, supporting the idea of scale invariance. However, in the presence of a conformal anomaly, this traceless property no longer holds, indicating that energy and momentum are not conserved in the same way across different scales. In essence, the conformal anomaly disrupts the expected behavior of the stress energy tensor, signaling a breakdown of scale symmetry. The conformal anomaly has significant implications in high-energy physics, particularly in the study of quantum field theories that describe the fundamental forces of nature. For instance, in theories that describe the strong nuclear force, the conformal anomaly plays a role in shaping how particles interact at very short distances. The strong nuclear force, which holds protons and neutrons together within atomic nuclei, is described by a quantum field theory that initially seems to exhibit scale invariance. However, the conformal anomaly shows that this symmetry does not hold at all scales, especially at extremely high energies or short distances. This breakdown of scale invariance influences the behavior of particles such as quarks and gluons, the building blocks of protons and neutrons, and affects our understanding of particle interactions within atomic nuclei. In cosmology, the conformal anomaly also has implications for theories describing the early universe. During the universe's first moments after the Big Bang, energy levels were extraordinarily high, and particles interacted in ways that are difficult to replicate under normal conditions. The conformal anomaly suggests that scale invariance did not hold in these early moments, meaning that particle interactions varied depending on the energy scale. This breakdown of symmetry could have influenced how matter and energy were distributed in the early universe, shaping the large-scale structures we observe today. Although we cannot directly observe the effects of the conformal anomaly from the early universe, studying this anomaly provides insights into how fundamental forces in particles may have behaved under extreme conditions. The conformal anomaly also plays a role in string theory, a theoretical framework that aims to describe all fundamental particles and forces as tiny, vibrating strings rather than as individual point-like particles. In string theory, conformal symmetry is essential for describing how strings interact with each other and with fields. Conformal symmetry ensures that strings maintain a consistent structure across different scales, which is important for maintaining a unified description of particles and forces. However, the conformal anomaly poses a challenge because it implies that this symmetry might break down under certain conditions, potentially affecting the predictions made by string theory. Addressing the conformal anomaly is, therefore, a key aspect of refining string theory and understanding how it might offer comprehensive theory of fundamental interactions. In addition to theoretical physics, the conformal anomaly has applications in condensed matter physics, a field that studies the properties of materials at atomic and molecular scales. Certain materials, such as graphene, a single layer of carbon atoms arranged in a hexagonal lattice, exhibit properties that are nearly scale invariant under specific conditions. In these systems, particles known as quasiparticles can move through the material in ways that mimic relativistic particles, meaning they behave as if they are almost massless and move at speeds close to the speed of light. However, due to the conformal anomaly, this scale invariance can break down when the quasiparticles interact with each other or with the material's structure. This breakdown affects the material's electronic and thermal properties, influencing how it conducts electricity and responds to external forces. Understanding the conformal anomaly in these materials helps scientists design new materials with unique properties and potential applications in technology. To understand why the conformal anomaly arises, physicists often rely on complex mathematical tools and equations, including the techniques of differential geometry, which describes how shapes and spaces bend or curve. In conformally invariant theories, the equations that govern particles and fields should ideally retain their form regardless of changes in scale. However, when quantum fluctuations are taken into account, additional terms appear in these equations, modifying the original relationships and breaking scale invariance. This breakdown indicates that quantum effects create situations where particles interact differently at various scales, even if they should theoretically behave the same under conformal symmetry. Another way to describe the conformal anomaly is through the idea of dimensional transmutation. In quantum field theory, dimensional transmutation refers to a process where a theory's parameters, such as particle masses or field strengths, change when observed at different energy scales. In a scale-invariant theory, these parameters should remain constant across scales. However, due to the conformal anomaly, the values of these parameters can shift depending on the scale of the system. This shift means that the theory's behavior changes depending on the energy or distance being considered, breaking the original scale symmetry. The conformal anomaly is also closely related to the study of conformal field theories, which are a class of theories in physics that are specifically designed to retain scale invariance under ideal conditions. Conformal field theories are used to describe various physical phenomena, from the behavior of elementary particles to phase transitions in materials. However, the conformal anomaly reveals that even these theories, which are designed to uphold scale symmetry, can experience symmetry breaking due to quantum effects. This finding has led physicists to explore new approaches to understanding scale invariance in the quantum realm, as the conformal anomaly suggests that no theory can maintain perfect scale symmetry in the presence of quantum fluctuations. The gravitational anomaly is one of the more abstract and challenging anomalies in physics, as it deals with inconsistencies between gravity and quantum mechanics, the two great pillars of modern physics. While quantum mechanics governs the behavior of particles at the smallest scales, from atoms to subatomic particles, general relativity, which describes gravity, provides our understanding of how objects behave on cosmic scales, from planets to galaxies and beyond. The gravitational anomaly reveals gaps in these theories, showing where quantum mechanics and gravity don't align, highlighting challenges in developing a unified theory. In physics, an anomaly generally refers to an unexpected breakdown in symmetry or conservation law. Specifically, the gravitational anomaly shows that certain mathematical structures and conservation laws that should hold under both general relativity and quantum mechanics don't work smoothly together when applied in specific high-energy situations. At the heart of this problem lies the difficulty of reconciling gravity with the quantum properties of particles, which creates inconsistencies in how fields and forces should behave. The gravitational anomaly is distinct from other quantum anomalies because it doesn't relate directly to electric or magnetic fields or particles like electrons or quarks. Instead, it involves space-time itself. General relativity describes space-time as a continuous fabric that can curve in the presence of mass or energy, while quantum mechanics typically describes particles and fields in discrete terms. The gravitational anomaly appears when trying to apply quantum field theory, a framework that successfully describes other fundamental forces, such as electromagnetism and the strong nuclear force to gravity. This approach works for many aspects of particle physics, but encounters fundamental problems when extended to include gravitational effects. To understand how the gravitational anomaly arises, we can look at the concept of symmetry in physics, particularly symmetries that should apply universally to both particles and spacetime. In quantum mechanics, symmetry often involves transformations or changes that don't alter the fundamental laws governing a system. For example, a system may have rotational symmetry if it behaves the same way regardless of how it's rotated. In the context of gravity, a specific type of symmetry known as diffeomorphism invariance is crucial. This symmetry means that the laws of physics should remain the same regardless of how spacetime is stretched or squeezed in different directions. Diffeomorphism invariance is a core part of Einstein's theory of general relativity, which describes how gravity arises from the curvature of spacetime. In quantum mechanics, There is a similar symmetry called gauge symmetry that governs the behavior of particles and fields. Gauge symmetry is fundamental to many successful theories, including those describing electromagnetism and the strong nuclear force, and it guarantees certain conservation laws. However, when quantum field theory is applied to gravity, it produces inconsistencies in maintaining gauge symmetry, especially in high-energy environments, such as those found in the early universe or around black holes. This inconsistency is a manifestation of the gravitational anomaly, the breakdown of symmetry that shouldn't happen but does because gravity behaves differently in the quantum framework. One way to understand the gravitational anomaly is by examining the concept of quantum fields on a curved background. In many quantum field theories, we consider particles and their interactions on a flat space-time background, which makes the calculations more manageable and predictable. However, when we try to describe quantum fields on a curved space-time, such as the curved geometry around a massive object like a planet or a star, the predictions start to deviate. Specifically, the energy levels and particle interactions become harder to reconcile with the underlying space-time structure, causing problems with conservation laws, such as the conservation of energy or momentum. In this way, the gravitational anomaly emerges as a conflict between quantum field properties and space-time curvature, indicating that our current methods cannot fully describe the behavior of particles in a gravitational field. Another aspect of the gravitational anomaly can be observed in systems where certain theoretical properties such as chirality and spin become important. Spin, a property of particles that can be imagined as a type of intrinsic rotation, plays a key role in quantum physics and determines how particles interact with each other and with fields. In a gravitational field, the behavior of particles with different spins can be affected in unique ways. For example, particles with half-integer spin, such as electrons, behave differently in curved spacetime than particles with integer spin, such as photons. This difference becomes especially noticeable in certain high-energy quantum states, where the interactions between particle spin and gravitational effects lead to unexpected shifts in energy or momentum, contributing to the gravitational anomaly. These anomalies are not merely mathematical curiosities, but point to deeper issues in combining quantum mechanics with gravity. General relativity works very well for describing large-scale structures, while quantum mechanics excels in explaining small-scale interactions. However, in extreme conditions, such as near a black hole or during the first moments of the universe, where quantum effects on gravity become significant, the gravitational anomaly highlights a breakdown in our understanding. The issue lies in the fact that the principles and equations of quantum mechanics do not naturally incorporate gravity as they do for the other fundamental forces. For instance, when gravity acts on very small scales, its effects don't fit neatly within the framework of quantum mechanics. One of the challenges physicists face is trying to develop a quantum theory of gravity to solve these inconsistencies. Quantum gravity aims to describe gravity at the smallest scales in a way that aligns with quantum mechanics and resolves anomalies like the gravitational anomaly. Many different approaches have been proposed for quantum gravity, including theories such as string theory and loop quantum gravity. In string theory, for example, particles are not considered as individual points, but rather as tiny, vibrating strings. This shift in perspective allows string theory to account for certain anomalies, including some aspects of the gravitational anomaly, by treating gravity as a fundamental force on the same level as electromagnetism or the strong nuclear force. Loop quantum gravity, on the other hand, attempts to describe spacetime itself as composed of discrete units, or loops, rather than a smooth continuum. This discrete model aims to address the gravitational anomaly by offering a new structure for spacetime that fits within quantum mechanics. In studying the gravitational anomaly, researchers also investigate how it affects physical processes on cosmological scales, where gravity and quantum effects both play crucial roles. During the early universe, conditions were extremely hot and dense, creating a situation where gravitational effects and quantum interactions were interconnected. In these high-energy environments, gravitational anomalies likely influenced how particles and fields behaved, affecting the formation of structures and the distribution of energy and matter. Although we cannot directly observe these processes today, studying the gravitational anomaly helps us refine theories about the early universe's conditions and the role of quantum gravity in shaping its evolution. Another related phenomenon is the Hawking radiation effect, which Stephen Hawking predicted. Hawking proposed that black holes, which are regions of intense gravitational pull, emit radiation due to quantum effects near their boundaries, known as event horizons. This effect is significant because it implies that black holes are not entirely isolated from the universe and may gradually lose mass over time as they emit radiation. The process of Hawking radiation is believed to involve interactions between gravity and quantum fields, and understanding it fully requires resolving gravitational anomalies. The study of these anomalies is thus directly tied to the behavior of black holes and other high-energy astrophysical phenomena, offering insights into how quantum mechanics and gravity influence each other in some of the most extreme environments. The Guage anomaly is a significant and complex phenomenon in quantum field theory that impacts gauge symmetries, which are fundamental symmetries involved in describing how particles interact with fundamental forces. These symmetries play a central role in the construction of theories that explain how particles behave at the smallest scales, dictating interactions such as electromagnetism and the strong and weak nuclear forces. The Guage anomaly reveals circumstances where these symmetries, which are crucial for consistent and stable interactions between particles, are unexpectedly violated. In classical physics, gauge symmetries are generally upheld, maintaining certain conservation laws and predictable behaviors. However, at the quantum level, the Guage anomaly shows that these symmetries can fail, leading to shifts in the conservation of currents and other quantum properties that were expected to remain stable. To understand the Guage anomaly, it is essential to start with an overview of gauge symmetry. In physics, asymmetry is a property that remains unchanged under certain transformations or adjustments. Gauge symmetry is a specific type of symmetry that applies to the gauge fields governing the interactions between particles. For example, in the case of electromagnetism, the electromagnetic field, which influences electrically charged particles, is described by gauge symmetry. This symmetry ensures that the behavior of particles, such as electrons and photons, remains predictable, following certain conservation laws like charge conservation. Gauge symmetry essentially means that certain properties, such as electric charge, remain invariant even if transformations or adjustments are made to the field's underlying structure. In quantum mechanics, gauge symmetry takes on a more complex role, as it provides the foundation for quantum field theories like quantum electrodynamics and quantum chromodynamics. These theories describe how particles interact through electromagnetic and strong nuclear forces, respectively. Gauge symmetry ensures that these interactions remain consistent, supporting the mathematical structure that underpins these theories. For instance, in quantum electrodynamics, Gauge symmetry is essential for ensuring that charged particles interact with photons in a predictable way. Similarly, in quantum chromodynamics, gauge symmetry governs how quarks, the building blocks of protons and neutrons, interact with gluons, the particles that mediate the strong nuclear force. However, the Guage anomaly introduces a fundamental challenge to these theories by breaking the expected symmetry. When a Guage anomaly occurs, it disrupts the conservation laws and symmetries that are supposed to govern particle interactions, leading to inconsistencies in the theory. Specifically, a Guage anomaly appears as a mathematical inconsistency that arises when trying to calculate the effects of quantum fluctuations on particle interactions. Quantum fluctuations, which represent the small, unpredictable shifts in energy that occur at the quantum level, can introduce new terms or factors into the calculations. These factors disrupt the gauge symmetry, leading to a breakdown in the expected behavior of particles and fields. One of the central aspects of the Guage anomaly is its impact on current conservation. In a theory with gauge symmetry, certain currents, which represent the flow of charge or other conserved quantities, are expected to remain constant over time. For instance, electric current, which represents the flow of electric charge, is expected to be conserved in an electromagnetic field with gauge symmetry. However, when a gauge anomaly is present, this conservation does not hold. Instead, the gauge anomaly introduces terms that cause the current to vary, breaking the conservation law and resulting in an unexpected imbalance. This failure of current conservation is one of the hallmark signs of a gauge anomaly, indicating that the theory's underlying symmetry has been compromised. Gauge anomalies have far-reaching implications in the field of particle physics, particularly in theories that seek to describe the fundamental interactions that govern the behavior of matter. For example, in the Standard Model of Particle Physics, which is the leading theory describing fundamental particles and forces, gauge symmetry is essential for ensuring consistent interactions between particles. The Standard Model incorporates three fundamental forces: electromagnetic, weak nuclear, and strong nuclear forces, each of which relies on gauge symmetry to maintain stability. When a gauge anomaly appears, it disrupts these interactions, potentially leading to inconsistencies that undermine the theory's predictions. The gauge anomaly can be illustrated through its impact on the behavior of particles with different charges and types of currents. In a theory with gauge symmetry, the types of particles that interact with a given force should remain balanced, with conserved charges and currents ensuring predictable interactions. However, the gauge anomaly disrupts this balance by allowing certain particles or currents to behave unexpectedly. For instance, in a gauge theory describing the weak nuclear force, the gauge anomaly could cause imbalances in the types of particles that interact, leading to shifts in behavior that violate expected conservation laws. This breakdown reveals that gauge symmetry does not always hold, especially under the influence of quantum fluctuations and high-energy interactions. In the context of quantum field theory, gauge anomalies are particularly problematic because they create mathematical inconsistencies in the equations that describe particle interactions. These inconsistencies arise when certain terms in the equations do not balance out as they should, leading to divergences or infinite values that make calculations invalid. When physicists encounter a gauge anomaly, it often means that the theory requires additional corrections or adjustments to restore consistency. In some cases, these adjustments involve introducing new particles or forces to compensate for the broken symmetry. For example, some extensions of the Standard Model propose the existence of additional particles that could help balance out gauge anomalies, restoring symmetry and making the theory consistent. Gauge anomalies also play a role in understanding high-energy interactions. such as those observed in particle accelerators. In these environments, particles collide at extremely high speeds, creating conditions where quantum fluctuations and gauge symmetry are put to the test. Under these conditions, gauge anomalies can become more pronounced, as the high energies involved intensify the effects of quantum fluctuations on particle interactions. Studying gauge anomalies in these environments helps physicists refine their understanding of gauge symmetry, providing insights into how particles behave under extreme conditions and revealing potential gaps in existing theories. One notable example of a gauge anomaly is the axial gauge anomaly, which appears in theories involving particles with chirality or handedness. The axial gauge anomaly is similar to the axial anomaly, as it involves shifts in the behavior of particles with different orientations. In this case, however, the anomaly specifically affects the gauge symmetry associated with axial currents, introducing terms that disrupt conservation laws for these currents. This phenomenon plays a role in theories that describe how particles interact through weak nuclear forces, showing that gauge symmetry does not always hold in these situations. The gauge anomaly also influences certain concepts in condensed matter physics, particularly in systems where particles exhibit behaviors similar to those observed in high-energy particle interactions. In materials with special properties, such as topological insulators, particles can move in ways that mimic relativistic particles, interacting with each other through forces that resemble those seen in particle physics. In these systems, gauge symmetry plays a role in determining the material's electronic and thermal properties, as it influences how particles with different charges interact. When a gauge anomaly occurs in these materials, it can disrupt the expected behaviors, leading to shifts in properties like electrical conductivity and thermal response. By studying gauge anomalies in these systems, scientists can gain insights into how gauge symmetry influences both fundamental particle interactions and practical applications in material science. To understand why gauge anomalies occur, physicists rely on complex mathematical tools such as path integrals, which describe the various possible paths that particles can take through space and time. Path integrals account for the fact that, in quantum mechanics, particles do not follow a single path, but instead explore all possible paths with certain probabilities. When gauge symmetry is present, these path integrals should ideally remain consistent, meaning that each path contributes to a stable, predictable outcome. However, when a gauge anomaly appears, certain paths contribute additional terms that disrupt this stability, leading to inconsistencies in the overall behavior of the particle system. These inconsistencies reveal the presence of a gauge anomaly, showing that the symmetry no longer holds. Another way to describe gauge anomalies is through the concept of Feynman diagrams, which are graphical representations of particle interactions. In quantum field theory, Feynman diagrams help visualize how particles exchange force carriers, such as photons in electromagnetic interactions or gluons in the strong nuclear force. In the presence of a gauge anomaly, certain Feynman diagrams exhibit loops or pathways that introduce additional terms, disrupting the expected conservation of gauge symmetry. These loops create divergences in the calculations, indicating that the theory needs adjustments to restore consistency. Studying these loop effects helps physicists identify and correct gauge anomalies, providing insights into how quantum fluctuations influence particle interactions. In addition to particle and condensed matter physics, gauge anomalies are also relevant in the study of theoretical frameworks like string theory. String theory aims to describe all fundamental particles and forces as tiny, vibrating strings rather than individual point-like particles. In string theory, gauge symmetry is a crucial component, as it ensures that strings interact consistently across different scales. However, gauge anomalies can disrupt this symmetry, introducing terms that affect how strings interact with fields and each other. Addressing gauge anomalies in string theory is essential for developing a unified description of particle interactions, as it helps refine the mathematical structure of the theory and provides insights into the nature of gauge symmetry in high-energy environments. Gauge anomalies also have connections to gravitational theories, especially in attempts to merge quantum mechanics with general relativity. In these theories, gauge symmetry plays a role in describing how particles interact with gravitational fields. However, gauge anomalies complicate this process by introducing terms that disrupt symmetry, making it challenging to create a theory that combines both quantum mechanics and gravity in a consistent framework. Studying gauge anomalies in the context of gravitational interactions helps researchers explore potential approaches to quantum gravity, providing clues about how gauge symmetry might operate in the presence of gravitational fields. Weyl symmetry is an elegant and powerful concept in theoretical physics that applies to systems exhibiting a specific kind of invariance under changes in scale. Named after the mathematician Hermann Weyl, this symmetry posits that certain physical systems should remain unchanged if their scale or size is altered. For example, imagine enlarging or shrinking every part of the universe simultaneously in a system with Weyl symmetry. This scaling would not affect the core physical properties. In the context of quantum field theories, where fields and particles interact in a highly structured manner across spacetime, Weyl symmetry initially appears to be an intrinsic part of the framework. However, as we transition from classical theories to quantum mechanics, the presence of quantum fluctuations disrupts this symmetry, leading to what is known as the Weyl anomaly. To understand the Weyl anomaly, it's essential first to recognize how symmetry operates in classical physics and how it becomes more complex at the quantum level. In classical mechanics, symmetries often lead to conservation laws such as the conservation of energy, momentum, and angular momentum, which describe quantities that remain constant despite transformations in time or space. Weyl symmetry is a more specialized form, focusing on the independence of a system's behavior from its scale. However, in quantum field theory, symmetries are not always preserved because the behavior of fields at the quantum level is influenced by fluctuations at extremely small scales. These fluctuations, tiny variations in the field's values that are inherent to quantum mechanics, do not necessarily respect the original symmetries present in the classical version of the theory. The Weyl anomaly specifically describes how Weyl symmetry is lost due to these quantum effects. In classical field theories, such as electromagnetism or general relativity, scale invariance often holds, implying that enlarging or contracting the entire system does not alter the behavior of the fields involved. However, when quantum corrections are introduced, this invariance can break down in subtle ways. Essentially, the introduction of quantum mechanics means that fluctuations within the fields interact with each other in ways that cannot simply be scaled up or down uniformly. These interactions create a kind of background noise that shifts the system away from its scale invariant behavior, even when the overall structure of the theory suggests it should remain unaltered. This breakdown of scale invariance becomes particularly relevant in certain quantum field theories and is one of the distinguishing features that separate quantum theories from their classical counterparts. Quantum electrodynamics, for instance, describes how particles interact with the electromagnetic field. At high energies or very small scales, quantum corrections introduce complexities that lead to a departure from exact scale invariance. In such cases, physicists observe that the predictions of the theory diverge from those made under classical assumptions of symmetry. The theory's scale begins to have a measurable effect, signifying the presence of the Weyl anomaly. The phenomenon of the Weyl anomaly provides an insight into the deep and intricate structure of quantum fields, especially those that are essential for the standard model of particle physics. The standard model, which unifies our understanding of the electromagnetic, weak, and strong nuclear forces, relies on a complex set of symmetries that dictate how fundamental particles behave. Yet the Weyl anomaly shows that certain symmetries expected to hold under ideal conditions do not hold universally. For example, theories that include massless particles, particles that should theoretically exhibit perfect scale invariance, are affected by the anomaly due to the quantum effects that perturb their behaviors on a microscopic level. These discrepancies indicate that while our theoretical framework can predict a high degree of symmetry, the quantum realm inherently complicates this picture, especially at high energies or extreme conditions. Interestingly, the implications of the Weyl anomaly extend beyond just high-energy particle physics. In the realm of gravitational theory, Weyl anomalies play a notable role, particularly in the study of black holes and cosmological phenomena. Gravity is typically described using general relativity, a classical theory in which the geometry of spacetime is influenced by mass and energy. However, if we attempt to combine general relativity with quantum mechanics, the Weyl anomaly introduces unexpected challenges. For example, as one approaches the intense gravitational fields near a black hole, quantum field fluctuations can affect the expected behavior of spacetime, violating scale invariance in ways that classical theories cannot explain. This anomaly also raises questions about the nature of spacetime itself. In attempts to unify quantum mechanics with gravity, a major goal in theoretical physics, the Weyl anomaly presents a recurring obstacle. Any successful theory of quantum gravity would need to account for the ways in which spacetime geometry interacts with quantum fluctuations, including the distortions introduced by the anomaly. For instance, in string theory, a leading candidate for a theory of quantum gravity, certain configurations of strings, hypothetical one-dimensional objects posited as the fundamental building blocks of the universe, are affected by the Weyl anomaly. Maintaining consistency within string theory requires that these configurations satisfy strict symmetry conditions. The presence of a Weyl anomaly can disrupt these symmetries, posing additional constraints on viable models within the theory. On a broader scale, the study of the Weyl anomaly has influenced the field of conformal field theory, a branch of physics that examines how scale and conformal symmetries operate in quantum systems. Conformal field theories are crucial to understanding phenomena at critical points, such as phase transitions, where matter changes state in a way that is independent of specific scales. Examples include the transition of water to ice, or the behavior of certain materials at very high or low temperatures. The presence of a Weyl anomaly indicates that even at these critical points, quantum effects may disrupt the expected behavior, revealing hidden complexities in how matter transitions from one state to another. Additionally, the Weyl anomaly finds applications in the study of the early universe, particularly in cosmology models that seek to describe the conditions of the universe at the time of the Big Bang. Near the beginning of the universe, where energy levels were extremely high, quantum fluctuations would have been profound, and scale invariance would not necessarily hold. The Weyl anomaly, in this context, suggests that the initial conditions of the universe may have been influenced by quantum effects in ways that classical models do not account for. These quantum influences could contribute to our understanding of cosmic inflation, the rapid expansion of space that occurred just after the Big Bang, and other large-scale structures observed in the universe today. Quantum anomalies present a profound challenge to our understanding of the universe, disrupting fundamental assumptions about how particles and forces interact across scales. In the classical view, the universe is governed by specific symmetries and conservation laws that provide consistency and predictability. Symmetry, for instance, ensures that certain physical properties remain unchanged under various transformations, like flipping left to right or scaling up and down in size. Yet, in quantum physics, these patterns don't always hold. Quantum anomalies, phenomena where expected symmetries break down due to quantum effects, highlight gaps in classical physics, exposing a hidden complexity in nature that defies straightforward explanation. In quantum mechanics, anomalies emerge because interactions at the smallest scales involve fluctuations that classical theories can't account for. These fluctuations are not just rare disruptions. They are inherent to how particles behave at the quantum level. When symmetry is lost in these conditions, it reveals a deeper layer of interactions that classical physics overlooks. The quantum anomalous Hall effect, for example, demonstrates this breakdown of symmetry in a striking way. This phenomenon appears in specific materials cooled near absolute zero, where they exhibit unique electrical conduction. Typically, electrical currents are affected by external magnetic fields, but in this case, the material itself develops an intrinsic magnetic-like effect, even without an external magnetic field. This anomaly is significant because it reveals that quantum properties of materials can change their behavior in ways that can't be fully explained by conventional physics, requiring new models to describe their effects. Another fascinating example of quantum anomalies is the Chiral Anomaly, which impacts particle interactions in high-energy physics and cosmology. Chirality refers to the handedness of particles, meaning that certain particles spin in specific directions. Classical theories suggest that this property should be conserved under certain transformations, but quantum mechanics reveals otherwise. In the case of particles in high-energy environments, like those produced in particle accelerators, their interactions sometimes exhibit a clear preference for one-handedness over the other. This preference hints at underlying mechanisms that were previously invisible, suggesting that fundamental forces may operate differently under extreme conditions, such as those present in the early universe. The Chiral Anomaly has implications not only for particle physics, but also for our understanding of cosmic phenomena, suggesting that the universe itself may have evolved in ways that break these basic symmetries. Quantum anomalies like these don't just add nuance to our understanding of known phenomena, they imply that our foundational physics could be incomplete. The gravitational anomaly, for example, appears when quantum mechanics interacts with gravitational fields, something that existing physics cannot yet reconcile. In classical physics, gravity is a predictable force defined by Einstein's general theory of relativity, a theory that describes the curvature of space-time due to mass and energy. However, when quantum field theory is applied in a gravitational context, as in the study of black holes, anomalies arise that disrupt the expected conservation laws. This gravitational anomaly is particularly perplexing because it implies that quantum fluctuations could distort the structure of space-time itself. It even points to possible modifications in how we understand black hole mechanics, where the intense gravitational forces may influence quantum particles in unpredictable ways. This anomaly suggests that at the extreme edges of physics, the established principles of quantum mechanics and general relativity cannot coexist smoothly. For theorists, it raises the possibility that a new, unified theory, quantum gravity, may be needed to explain the fundamental workings of the universe. Such anomalies also complicate our understanding of the early universe. The conformal anomaly demonstrates how symmetries involving space-time scale break down under quantum effects. Conformal symmetry implies that a system remains invariant when both space and time are scaled simultaneously, which in theory should apply to the entire universe, particularly during its initial conditions following the Big Bang. However, the conformal anomaly reveals that even in such a vast context, quantum fluctuations cause deviations from this expected symmetry. By studying this anomaly, scientists aim to understand quantum fluctuations during cosmic inflation, the period of rapid expansion that occurred right after the Big Bang. These fluctuations may have seeded the large-scale structures we observe today in the universe, meaning that quantum anomalies could directly impact cosmic evolution. The breaking of symmetries at the quantum level also drives new experimental and theoretical research, as physicists attempt to probe and measure these anomalies with increasing precision. One area of focus is the study of topological materials, unique materials that exhibit quantum properties not found in traditional substances. These materials are not merely conductors or insulators. They host quantum states that are resistant to environmental disturbances, making them ideal candidates to observe quantum anomalies in controlled environments. For instance, the quantum anomalous Hall effect observed in topological insulators provides insight into how quantum mechanical properties can lead to unusual states of matter. Experimental work on these materials could not only validate theoretical predictions, but might also lead to the development of new technologies in quantum computing and sensing. These topological materials, therefore, serve as laboratories for observing quantum anomalies firsthand, allowing physicists to test and refine theoretical predictions about symmetry and its breakdown. At the forefront of quantum research, questions around anomalies are pushing physicists to rethink how we define and measure fundamental forces. One major challenge is the lack of a unifying theory of quantum gravity that successfully incorporates the principles of both quantum mechanics and general relativity. Current research in this area examines potential candidates like string theory and loop quantum gravity, both of which attempt to reconcile these opposing frameworks. String theory, for instance, proposes that fundamental particles are not zero-dimensional points, but one-dimensional strings. Under this theory, the Weyl anomaly, another type of quantum symmetry breaking, must be meticulously managed to maintain the mathematical consistency of the theory. The study of quantum anomalies within string theory and similar frameworks offers the possibility of bridging quantum mechanics with gravitational physics, hinting at a deeper, perhaps more accurate description of space-time and matter. Another exciting avenue of research involves studying how these anomalies could reveal previously hidden forces or particles. Anomalies have occasionally been used as indicators of new particles that were later confirmed, like the discovery of the Higgs boson. Some physicists hypothesize that anomalies might signal the existence of other undiscovered particles, such as those that could make up dark matter, the mysterious substance thought to compose a significant portion of the universe's mass. Since dark matter does not interact in ways that allow us to detect it directly, anomalies could provide indirect evidence of its influence on other particles, potentially guiding future experiments designed to detect it. Additionally, quantum anomalies continue to challenge the way we understand conservation laws, such as the conservation of energy and charge. By studying anomalies that break these conservation laws under quantum effects, physicists hope to refine our definitions of these laws to account for quantum interactions. New experimental tools, like high-energy particle colliders and advanced telescopes, are now being used to observe high-energy particles and cosmic phenomena that may exhibit these unusual behaviors. Each new experiment brings a wealth of data that could either confirm or contradict existing theories, providing a constant source of feedback and refinement for theoretical physics. Ultimately, quantum anomalies confront us with open questions that continue to shape and reshape physics as a discipline. Are these symmetry violations signs of a deeper structure we have yet to discover? Could anomalies reveal unknown forces or dimensions? How do they reshape our understanding of space-time, energy, and matter? These are the questions driving physicists today, questions that lead directly to the boundaries of what we know about reality itself. The exploration of quantum anomalies is not just an intellectual exercise, but a journey into the heart of the universe's mysteries. As research in theoretical and experimental physics progresses, each breakthrough in understanding these anomalies brings us one step closer to revealing a more complete picture of the universe, an image that is bound to be as complex and captivating as the quantum world itself. This concludes our video. We hope you enjoyed the content and found it informative. If you did, please consider subscribing. It's free for you, but helps support our channel. Thanks for watching, and we'll see you in the next video.